application of laser-based analyzers in steel industry. So I will try to maybe present more from the actually analyzer side rather than application, because you already presented what is the goal for usage of the gas analyzers. So first of all, some brief information about our company. So we are a small medium enterprise based in Poznań in Poland. We manufacture laser-based gas analyzers for various industrial applications. So steel industry is something which we actually started very recently. But we mainly focus on applications in industries where traditional gas measurement is difficult because, say, of high temperature or difficult conditions, or where, for example, the high fast response times is very necessary, as well as low maintenance. And so we mainly work in power industry, petrochemical industry, chemical industry, wood industry, and as I mentioned, also steel. We have in-house technology and R&D department on site, so we can also make a customized solutions for customers if there is a special request. We mainly work on as export. 90% of total revenues accounts for export, and 10% for internal market. And so we have different kinds of gas analyzers. They're all based on laser technology. Today I will only talk about so-called in situ analyzers, so the ones which are used basically directly on the process, so without any sample conditioning. But just to mention, we have also open path analyzers, so we use laser technology to measure around the fence, so we can measure, say, the leakages from different industries on the up to 1 kilometer distance. And finally, the extractive analyzers, more like traditional type, where the sample is extracted from the, say, pipeline with some sample conditioning system, and then the analysis is done internally in the analyzer. It's more like gas chromatograph, but it's based on laser technology. But it's a bit outside of the scope, so let me continue. So if it comes to the in situ analyzers, as I mentioned, the systems are relatively easy mounted on the process. It can be a chimney, it can be a furnace, it can be any pipeline. And then you do it with different kind of flanges. So in Europe, we have DN50 flanges, but we have also ANSI standards, say, for American market, and also GIS for Asia. And that's basically just a matter of configuration. But the idea is that you measure directly in the process. So you have a very fast response time to whatever happens to the flue gas, or the gas you measure. And that's why we can have different applications for control. So basically process control of different industrial processes. Typically combustion control. It can be also safety application, like you basically monitor some process and monitor some gas which is critical to the process, like carbon monoxide and oxygen. The oldest application was actually SCR, so selective catalytic reduction, so the denitrification process in the power plant. But there are many different applications. Yes, so that's and in the steel industry also try to use our systems already. And now what we do in multiple is very, say, advanced type of application we want to obtain. So the principle of operation, the physics is very simple. So this is based on the absorption technology. The system consists of two units. It's a transmitter unit which sends the light from one side of the process to the other, so shining the light exactly through the process. And then what we do is we measure the absorption of the gas. So the gas acts like a filter, basically, which selectively reduces the light intensity after passing through the process. So that's in principle very simple physics, but the difficulty, practical conditions are that normally you don't only have the gas of interest, you have also a lot of dust. For example, if you burn coal in the coal-fired power plant, there's a lot of dust which scatters light more than actually the molecules absorb. So but the analyzer is capable of distinguishing between one and the other. So it's very selective and very sensitive. So absorbances down to 10 to minus 7 in relative units. So compared to FTIR, this is already 3 orders of magnitude. So one of the typical example of the application is combustion control. So in the beginning, we only use the oxygen system. So we are measuring oxygen basically directly in the boiler above the fireplace to try to optimize the combustion process in real time by using our signal Then we also added carbon monoxide analyzers, so you can actually try to optimize combustion a little bit closer. And that's what's typically used in the boilers. So not in the steel plants, but say a bit lower temperatures, say in the power plants or in some chemical processes, and anywhere you have a combustion. And it seemed to be already well-proven technology and accepted. So the drawback of the EC2 lasers are that they are basically very selective, but you need basically one analyzer for one gas. So what we did in 2018, we released a model which combines two lasers into one analyzer. So the form factor is basically the same, but you are measuring both carbon monoxide and oxygen and water in one analyzer. And this has already been proven in, say, smaller stacks and for combustion optimization in smaller boilers, I'm sorry, and also in some power plants. And then what we try to do is to we ask ourselves the question, can we use it also for different processes like steel industry? And that's what we did also a couple of years back, but for a little bit simpler case when we had a hot rolling mill and optimize the furnace conditions by either measuring the oxygen or carbon monoxide or both. And the only difference with the boiler was that here the temperatures were up to 1350 degrees. But so the conditions were slightly more difficult, but it's also proved that this technology can be applied to the steel industry. And there are some technical issues here that we have to add some additional cooling devices if the ambient temperature is above plus 55 degrees. But nevertheless, it proved to be working fine. So the next step was so that except for combustion control, can we use something else? Can we use some other type of optimization? So what we did is also we had the installation for the optimizing of the fuel, also the measurement of the fuel composition of the gas which feeds the furnaces. And that was done also, for example, in the case when the gas used for the reheating furnace is mixing different type of gases available in the plant. And these components can be changing in time. So the customer wanted to have the knowledge of the real-time composition of the gases. And we deployed two analyzers, one measuring methane, ethylene, and water vapor, and the other carbon monoxide, CO2, and H2S. So basically this was enough for customer to already get some additional knowledge in real time about the gas feeding the furnace. And now, finally, what we try to do in multiple projects, so together with LDL and Ursula and Ayman, is to have a very advanced analysis of what's going on in the reheating furnace. So as Ignacio already showed, there is a plan to deploy analyzers in 3 different points, as well as not only measure the carbon monoxide and oxygen, but also extend it to temperature, water vapor, and CO2. And also NOx, it's not shown on the graph, but basically to have a very complex analysis in the real time of the gas composition. And by means of this, we hope to save the energy, basically by optimizing the combustion process really close and more precise, but also to reduce the waste in form of basically some waste material. That's what also Ignacio mentioned in his presentation, that if the combustion is not sufficient or in the conditions in the furnace are not optimal, then it produces waste. So that's already, the project has basically started recently. So now our systems are installed at the LDL. And I hope the first results can be expected, I think, in September already. And so we are all very curious how it will all work and in the closed loop system, because the idea is also to use our outputs of the gas concentration in the edge computing device. That's the whole idea about the multiple. And also I hope with combination with the camera information to have a more profound control of the furnace condition. So this is really something new which never had been tried before. So we are all very excited. But from our part, from the just analyzer part, we think that just to summarize, basically in situ technology as such can provide really fast response times, because this was already proven, and which in general can be used in the fast closed loop control, because basically most of our clients use our analyzer in the fast loop control. So this is really something really standard in the power plant today. And also the temperatures, there is basically no limit of the high temperature for the spectroscopy. And then basically because we use laser, it's very selective and sensitive. So it's not like the non-dispersive techniques. And last but not least, these analyzers are also made that we have 24/7 operation. They have a self-calibration feature, which basically gives you a low maintenance, low cost of ownership in the end. And mechanically, they're also, suitable for this type of environment. And we also have a possibility to deploy them in the hazardous areas if necessary. For example, for zone 1 or even zone 0.